Week 2011, you guys are on your text page 359, blue notebook page 313. We're going over lesson 6.5. I may put in lesson 6.6 also. You guys have done this before. The only difference is we're using a different type of graph. You guys were used to graphing a parabola and shifting it around the page. Now we're using that sine function that so many of you drew so well on that quiz, and we're moving it around the page. You're welcome. So, the book uses different letters. The book refers to shifts in sine function as sine x minus c. I've replaced it with h. Does anyone remember what h does when we're moving a parabola? Nino, left or right? So they use the letter c. So I've replaced it with h. What does that mean is going to happen to the sine function if I have a number in for h? What do you think is going to happen to that wave? Left and right. Simple as that. They also use the letter d. Sine x plus, and they have the letter d. I've replaced it with k. Do you guys remember what k does? Up and down. Not diagonal. Up and down. So, if there is a number in the place of k, that means the sine wave is going to move up and down. And, you know what? Let's throw in the other one. Oops. Oh, that'll go away. All right. The other one is if we have A. Does anyone remember? And I think they actually use the letter A. Let me make sure. Yeah, they use A. Good. Does anyone remember what A represented with a parabola, Thomas? Yeah, so it's stretching it. It's the exact same thing. This is going to go with stretching the wave. Okay? So, we're not going to use the letters C and D, so your textbook is going to have them. I want you to remember, anytime your textbook refers to the variable C, over here, we're just going to call it H, just because we're familiar with what H does. We've done this before with parabolas. Same idea with D. They've used the letter D. We're going to use the letter K, just so we can relate it back to parabolas. And the book refers to A. We already know what A does with parabolas. You guys okay with that right now? So we're switching the letters that the textbook uses so that you guys have some familiarity with this. Okay. Let's jump right to this and see if this will help. Okay, so I have here a sine wave. Okay. We're going to call it A1. Uh-oh. Why did it stop? Oh, there we go. Call this 1. No. Use B and C. Oh, you know what? X is in radians. I got to change that too. Why does stuff work? Maybe we can't use this. Oh, yes, I am recording. Oops. All right, scratch that idea of the other one. We're just going to make our own graph. So, what you guys were to have drawn yesterday, if you guys remember, I asked you for the sine function, sine at x. Okay? So you're to draw that entire wave. If you guys remember the key points, we had 0 and 0, 1 and 90, 0 and 180, negative 1, 270, 0 and 360. What would the pattern be? At 450, where would I be? 1 again. Good. Okay? And on the way back, the opposite. Negative 90, right? Negative 1. Negative 180, 0 again. Negative 270s, positive 1. And then negative 1 again. So if we are to connect these dots, I'll add the stop there. Okay, so this is what our normal sine function looks like. We're going to call this our theoretical model, skeleton model, whatever you guys want to call it. If you guys remember when we did a parabola, we referred to the parabola that was right at 0 and over 1, up 1, over 2, up 4. Looks like that. That was our skeleton model, and then we constantly moved that model. Okay? It's the same idea, but we're going to be moving this wave instead. So it's not a U shape. We're going to be moving this entire wave when we do something. So the first one we'll deal with is a movement of K. K is usually the easiest to recognize. Okay? Do we have examples in this one? What's that? K, I'm going to show you again. K is up and down. So if you have a function sine x, I don't have a lot of room there. Let's write that smaller. F at x equals sine x. And I'm going to put plus 3. What do you think is going to happen to this wave? K represents plus 3 now, okay? Thomas? Yeah. All we're doing is moving this wave up 3. So as long as we can draw our normal one, what we have right here, I take all of those major points, and I'm just going to shift them up 3 because we're a positive 3 along the y-axis. So when I'm at 0, normally, that's going to go up to 3. 90 is at 1. Well, I move that up 3. I'm going to be at 4. Why did the graph go like that? Oh, because that's not 3. There's 3. Sorry. Guys, you guys stay on me there. I was 1.5. Jeez. Okay. 180, 0. 0 plus 3 is 3. Negative 1 plus 3 is 2. 0 plus 3 is 3. 1 plus 3 is 4. And we can continue that pattern back the other way. Negative 1 plus 3 is 2. 0 and 3, 4, 0, and 2 again. And there you go. We now have the exact same wave. It hasn't stretched at all, hasn't moved left or right. All that happens is it is shifted upwards 3. What if that number had been negative 4? If I had an equation that looked like this, f at x equals sine x, and we're going to write in green as negative 4. What would happen to this wave? Yeah, exact same thing. It'd just be shifted down 4. Do you guys want me to draw for you? You okay with that? Okay. That's movements of K. I'm going to quickly, actually we'll keep it on. Next one we're going to deal with is our H. So right now we're doing them one at a time. I've only used the K shift. Now we're going to use the H. Okay? Does anyone remember what was special about H? If H was negative 5, which way would we have moved? Right 5. And if it was positive 5, which way would we have moved? Left. Okay. Now the only difference here is we're not going to deal with the numbers 1 and 5. We're going to be using degrees because the x-axis is measured in degrees. So our movements are going to usually be 90 or 180 or maybe even 45. Okay? So let's say I have f at x is equal to sine, now we're in brackets, x, we'll do it in blue, plus 90. Okay? So I have plus 90. What does that mean? We only have an h in this equation. So what's going to happen to our original one, the one we've drawn in black? How many? 90 degrees. So we're just going to move that exact same wave left 90 degrees. So if I'm at 0 and 0 in degrees, I move back 90 degrees. My y is still at 0. my 90. If I subtract 90, so here I'm at 1, I'm going to move left 90 degrees. So I take all of our major points and move them left 90 degrees. What do we have here? There and there. So we'll connect the dots. And what would the next number be? If I'm at 450 degrees, what is my y going to be in that case? It's going to be 0. That would be our pattern. We swoop back down. Okay? So our blue wave represents this function here, f at x equals sine x plus 90. If that had been, so we'll make one a little tougher. If that had been f at x equals sine x, ready, minus 45. What would happen? Thomas? 45. Okay. Now what would be 45? Our scale is measured in 90s, it looks like. Or sorry, every 2 is 90, so it would be just 1 block instead of 2. Do you guys want me to draw that one? Yeah, I think maybe I should draw this one. Might be a little tougher. I like Ryan's idea. We'll do it in the dotted. Okay. So if I'm at my normal one, 2 steps is 90. That means 45 degrees is just going to be a half step. So everything moves a half step, or 1 block we would call it, to the right. Wait, there we go. So when we take a look at this, using the dotted one. You guys notice it's only been shifted to the right 45, so it's a small shift. Does that make sense to you guys? I know it's getting kind of convoluted in the middle there. Can you guys see that shift? Okay, finally we're going to deal with A. In our original one, A is, because there's no number there, what do we assume A is? Just a 1. In this case, A is 3. So, this is the tough part about A. You're going to be taking whatever y value you're at, and you're going to be multiplying it by A. So, when I'm at 0, and I multiply by our new A, which is 3, what do I get? So, my y-coordinate is still 0. When I'm at 90, and my y-coordinate is 1, I multiply by 3, what do I get? 3. So my new y-coordinate is 3. So our wave hasn't moved left or right or up or down. All it has done is stretched. So when I'm at 90, I'm now at 3. Once again, 180, our y value is 0, so I'm at 0 again. But at 270, my y value is negative 1. So when I multiply that by 3, what do I get? Negative 3. So all of our 0 points are the same. Anything that is off of 0 has been stretched by a factor of 3. This would be the toughest movement of everything we're doing. So if you take a look at this wave, the wave hasn't moved left or right or up or down. All it's done is stretch by a factor. So this one goes up 3 times as much. So its peak is 3 times as high, and its trough is 3 times as low as our normal equation. The same idea would be if we were less than 1. If I was less than 1, it would be compressed by that factor. For instance, if it was a half, I would only go up a half instead of an entire 1.
So